The Higgs boson appears to contain no traces of new physics. Although the discovery of the Higgs boson was announced in 2012, physicists still have not understood its properties with satisfactory accuracy. Although after 12 years of research we know a little more about this particle, it seems that it does not contain any elements of new physics outside the Standard Model. In 1964, physicist Peter Higgs, who died in early April, proposed the existence of a new particle. He theorized that there must be a subatomic particle that would explain how other particles gain mass. In 2012, the Large Hadron Collider, LHC, managed to detect such a particle, which came to be called the Higgs boson or the God particle. Since its discovery, physicists have been trying to understand the properties of this very important elementary particle as precisely as possible. This task is extremely difficult due to both experimental challenges and numerous computational obstacles. The discovery of the Higgs boson is believed to be the largest discovery made at the Large Hadron Collider. The Nobel Prize-winning achievement is explained by, among others, existence of mass. The Higgs boson is a fundamental element of the Standard Model, a set of theories describing the basic elements of the structure of the universe. The Standard Model is one of the most important theories in modern physics. It is a theoretical framework that describes nature at its most fundamental level. Scientists use it to describe all the known elementary particles in the universe and the forces through which they interact. The model began to be developed in the 1970s. However, scientists are aware that it is limited, and although it is our most comprehensive and accurate model for particle physics, it has gaps that prevent it from explaining everything, such as gravity, what dark matter is made of, or why in the universe we observe much more matter than antimatter. Scientists are looking for particles that behave differently than expected from the Standard Model predictions to help explain some of these mysteries. They hoped that the Higgs boson would allow the Standard Model to be extended. But this particle turned out to be so difficult to generate and observe that, despite 12 years of research, its properties are still not known with satisfactory accuracy. Recently published works by a group of physicists from the Institute of Nuclear Physics of the Polish Academy of Sciences, V2Zvk, in Krakow, V2Zvk University and Max Planck Institute für Physik, MPI, from Garching near Munich describe the properties of the Higgs boson in more detail. These findings suggest that there are no signs of new physics in the studied mechanisms responsible for the formation of Higgs bosons. The results and description of the research were published in the journal Physical Review Letters / For a physicist, one of the most important parameters related to each elementary or nuclear particle is the cross-section for a specific collision. It carries information about how often we can expect a given particle to appear in collisions of a selected type. We focused on the theoretical determination of the cross-section value of the Higgs bosons in gluon-gluon collisions. They are responsible for the production of approximately 90% Higgs, traces of whose presence were registered in the detectors of the LHC accelerator, explains Dr. René Poncelet in a statement published on the V2Zvk website. The essence of our work was the desire to take into account certain corrections when determining the cross-section for the production of Higgs bosons, which, due to their seemingly small contribution, are usually omitted, because ignoring them significantly simplifies the calculations. For the first time, we managed to overcome mathematical difficulties and determine these corrections, notes Professor Michael Zikin from RWTH. The importance of the role of higher-order corrections in understanding the properties of the Higgs bosons can be demonstrated by the fact that the secondary corrections calculated in the article, seemingly small, contribute almost 1/5 to the value of the cross-section sought. For comparison, third-order corrections are at the level of 3%, but reduce computational uncertainties to only 1%. What was new in this article was the inclusion of the influence of beauty quark masses, which led to a small but noticeable additional shift in the value by about 1%. It is worth recalling here that the LHC collides protons, i.e. particles consisting of 2 up quarks and 1 down quark. The temporary presence of quarks with larger masses, such as the beauty quark, inside protons is a consequence of the quantum nature of the strong interactions that bind quarks in the proton, we read in the release. Poncelet adds that the cross-section values found and those measured at the LHC are actually the same. Of course, taking into account calculation and measurement inaccuracies. So it seems that the mechanisms responsible for the formation of Higgs bosons we are investigating do not show any signs of new physics, at least for now, he sums up. The IFJPAN statement noted that these findings do not exclude new physics in the phenomena accompanying the birth of the Higgs bosons. The results of experiments from the 4th research cycle of the Large Hadron Collider are awaiting analysis and may change a lot. The increasing number of observations of new particle collisions may allow the measurement uncertainties to be narrowed so much that the measured range of allowable cross-section values for the production of Higgs bosons will no longer coincide with the one determined by theory.